and welcome to the second coding session. Today we will be talking about convolutional neural networks, a big topic, especially in the field of AI in the past decade. And so let's start with the introduction and theory part. And today is session 2. So as I mentioned earlier, we will be talking about convolutional neural networks. And this, if you're interested, this is basically covered in chapter 6 of the book I mentioned previously. Let's start a little bit with motivation. Last time we discussed multi-layer perceptron models, and we showed an example where the MLP was trying to learn from an image. So imagine here you have a training sample, which is an image of the fashion MNIST dataset, and here it shows a t-shirt, basically. And what we did to pass this image into our MLP was to flatten the image. So we took every column and just stacked them onto each other until we had one very long vector. But what we did by doing so was destroying the inherent structure and the spatial information of the data. And this is not really desirable because we might get very important information of where certain input features were located in that image. Another point that I would like to raise is that the number of required parameters might get very prohibitively large quite quickly because you can imagine if we have an image which is in the megapixel size, then we would have millions of input features. And since MLPs are dense, so each neuron is connected to the next neuron in the next layer, that would require a lot of parameters. And the question becomes, how do we reduce the number of parameters, and how do we make sure we don't destroy the um, inherent structure of the image data? And one way to think about it, and it's in the book and it's quite funny, is we can understand how to solve the problem by this really fun kids book. I'm not sure if you're very familiar with that, but I grew up with those books, which are called Where is Waldo? And this book is full of images, and somewhere in this picture, there's Waldo. And I've already found him for you. He's here in the middle. And the goal is always to find Waldo in that image. And let's imagine we wanted to create a Waldo detector, so to speak, which screens little patches of the image to find Waldo. So it will start here on the top, and then it will slowly scan the image from left to right, let's say, and then from bottom and down. And what it would need to do is to assign a score for each patch, whether or not there was Waldo. And there are two important design principles which we can derive from this thought experiment. The first one is translation invariance. And simply speaking, what it means is that it doesn't matter where Waldo is located. So if it's here or here, our detector should give the same output for that given patch. So we're only interested where Waldo is and not necessarily where he is. Sorry, we only need to care about what he looks like and not necessarily where he's located. The second principle is locality. Let's assume the detector had a very large search window. What that would mean is that the detector would have a lot of noise as input as well, and it wouldn't be able to maybe even find Waldo because there's too much noise. So the search window itself should be as small as possible so that we don't concentrate on unrelevant regions of the picture. And we can derive the full convolutional layer from the multi-layer perceptron equation that we showed previously. This is given here on the right side, where we have H, which is the hidden representation. We have U, which is the bias, and then X are the inputs, so the image in our case, and V would be the weight or the parameters of our model. We can also call it as a weight. And from going from this upper equation here to the lower equation, we only need to do a little bit of a cosmetic trick, and we are just re-indexing here K and L into A and B. But if you do the math yourself, I'm pretty sure you can convince yourself that these two equations are equal. Next, we will add the translation invariance. And what that means is that V and U, they don't really depend on the pixel location I and J. And what that means is that here we can just remove here this I and this J, as well as this I and this J here. So we simplify the equation and we arrive at this third equation here. And the second principle we already discussed is locality. And what that means is that for each initial pixel, we only need to consider the neighboring pixels within a specified neighborhood, and we can choose what this neighborhood is. It's called delta here, but it basically can be any number we wish it to be, and the bigger that delta is, the more pixels we will consider. And V in this form itself is then known as the convolutional kernel, or as a filter in the literature. And going from this to a full image, there is only one last little detail missing. As you might know, images have 3 channels because they tend to be represented as a RGB, so red, green, and blue. And all we have to do is to add a dimension here to our tensors. And C here would be the input, the dimension of the input. So if we are starting from the raw image, that will be these 3 colors, but it could be any number as well. And D would be the number of output channels that we desire. We can actually choose how many output channels we want to have, and we will see how it's constructed later on. Just as a quick side note, these dimensions are also called feature maps. And yeah, what we just did is basically derive the full convolutional layer. So this equation is basically it. So everything we will discuss from now on is based, or is going to use this type of layer in our neural network. Here I've given the full equation, but maybe it's a little bit difficult to imagine what that filter does and how it works. So the simplest way to understand it is by a quick example. And as a side note, even though they are called convolutional neural networks, what we are doing, strictly speaking, is cross-correlation. And these operations are quite similar and only differ in flipping the kernel tensor, if I'm not mistaken. But this is maybe going a little bit too much into the details. So we will just accept that they are called convolutional neural networks, but they are doing cross-correlation. And what the CNN model has to do is to learn the kernel parameters from some training data. So let me give a quick example. Let's imagine that this is our input. It could be, let's say, an image on a grayscale from 0 to, let's say, 10. So this is our image. And then we have our model, or the model's kernel or filter. And this will be the output. And how it works is that we are going to multiply this 0 times this 0 plus this 1 times this 1 plus this 3 times this 2 plus this 4 times this 3. And this should give us the 19 here. And what we're going to do then is to move the kernel by 1 location to the left. So we are now considering this for input pixels, and the kernel stays the same. And if we do the same operation again, so 0 times 1 plus 2 times 1 plus 2 times 4 plus 5 times 3, we will get this 25. And then we can continue and just put our filter 1 pixel below on the left, and then move it once to the right, and then we will get this output tensor. So this is basically how the cross-correlation operation works. However, as you might have noticed, there is a very important side effect. The output dimensions will shrink, at least the spatial dimension. And one very nice solution is to pad the image on the outer edges. And what that means is that if we started from this tensor again, we will just add zeros on the outer edges. And when we do the cross correlation with the kernel, our output didn't shrink as much as the initial operation. So padding is a very effective solution to control the height and the width of the output, basically. And one interesting thing to note is that kernels often have odd heights and weights, such that the dimensions behave quite nicely when used in combination with the padding. So most of the time you will see convolutional layers which use odd filters. So one times one, 3 times 3, 5 times 5, and so on. Another thing we can do is move the kernel over the input image, but not necessarily 1 pixel by 1 pixel. We could choose how we want to move it. So here's an example where we would move it with a stride of 3 and 2 for height and width. So here we would go here. We will start with this 0, 1, and then we move by 2. So 1, 2, and then we consider this 4 pixels here. And here we don't have enough pixels, so there's nothing we can do about it. We just move on. And then we said we're gonna go 3 pixels down. So 1, 2, 3. And then the next 4 pixels will be those 4 pixels here. And then lastly, these 4 pixels here. So this is how we will get the output here with this specific stride. Lastly, we also need to talk a little bit about multiple input and output channels. I already gave an example of where we need to use multiple inputs. So for images with RGB, we would have 3 matrices, let's say of this size, and we need to somehow combine them. And the solution is to have multiple kernels, one for each dimension, do the cross correlation, and at the end add them all together. And for the output channel, what we will do is stack several kernels together again to go from a local to a global representation. And here I've just picked out the equation from the official PyTorch documentation. And as you can see here, we have the C out channel. So this is the equation for one single output channel. It has a bias, and then it will be a sum over all of the input channels. So basically what we have done here. It's just that if we want to have more than just one output dimension, we have to create this, or we have to duplicate this equation for each channel itself. And I already mentioned that there is something such as a 1x1 convolutional layer. It might seem a little bit strange at first, but they are basically fundamental because they are equal to the pixel-wise multi-layer perceptron over the channel dimension. And I think the figure on the right shows that quite nicely. Let's say we had this kernel here, this light blue one. What it will do is take the first upper left pixel of the input, and then it will add them, and it will create the first output dimension feature map, basically. And then we can have a second one and the third one. We can have as many as we want. But the important thing is that it controls the number of input dimensions versus output dimensions, so to speak. So we are able to control model complexity with these 1x1 convolutional layers. And we're almost finished with all the ingredients. There's really just one missing, and this is max and average pooling. There are two main issues with convolutional layers. The first one is that they are quite sensitive to the location, and this is by design, as we discussed during this session. And the other one is that the spatial information can be very high dimensional. So your height and width can grow indefinitely if you wanted to. So we need to have a solution to combat those two issues. And the simplest one is to use pooling layers. And what pooling layers will do is that they downsample the spatial resolution, sometimes by quite a bit, depending on how you define them. Here's an example of a 2x2 max pooling operator. And if we apply it on this input matrix, it will just check what is the maximum value and set this as the output. So here that will be 4. If we consider these 4 pixels here, that will be the 5 here. And if we consider these 4 here, that will be the 7, and here the 8. So here we would have our output. There's more than just max pooling. One could also do average pooling, where the operator will just calculate the average of all the entries. And one important point is that the channel dimension doesn't change in this case. So if our input data has 3 channels, in this case it has only 1, but if it had 3, then the output also would have 3. And these pooling layers also can have stride and padding, since they work very similar to the convolutional filters. So there's nothing stopping us from moving the operator 2 pixels at a time or so. And with that, we are ready to construct our first CNN. And I will quickly discuss the first published CNN proposed by Jan LeCun and all. He's currently the head of AI at Facebook, if I'm not mistaken. And the model that he was proposing was trying to solve the handwritten digit recognition problem. And in this problem, what we have is a 28x28 grayscale image of a handwritten digit. And then we have these convolutional layers, which extract features from this input image. We have a pooling layer, as we have seen before, then again, convolutional layer, and then pooling layer again. And at the end, we have 3 dense layers before going out. And you can see here that the last output dimension is 10, which is for the 10 digits one could classify the handwritten digits too. And what's interesting to note is that this is the first CNN which matched the performance of support vector machines on digit recognition task. And this model was introduced in ATMs to exactly do what it was supposed to do, so recognize handwritten digits. And the book claims that they are still in use today, which is kind of interesting, since the model itself is really not that difficult to implement, at least today. Probably, yeah, it was developed in 1998, so I guess at that time it was more troublesome to implement all these layers from scratch. But with all these frameworks we have, like TensorFlow, Keras, or PyTorch, basically building this model isn't too much of trouble. And yeah, the model basically interleaves convolutions, the nonlinearity we discussed last time. So in this case, rectified linear units, as well as pooling layers. And what's important to note is that LeNet decreases the spatial resolution. So these maps here get smaller and smaller, but the channel dimensions grow. And this is how modern CNNs are built. So the spatial resolution will tend to get smaller and smaller in later layers, but the spatial resolution gets bigger and bigger. We can also represent these CNNs in a more compact form using compressed notation. For example, this is the compressed notation for LeNet. So you can verify later for yourself that this notation is exactly the same as the model of the previous, on the previous slide. But those are strictly equivalent. It's just that it's much easier to see what's happening if it's noted in this way. Then, do we have enough time? Let me just check. Yeah, we have a little bit of time to talk about modern convolutional neural networks. So these are networks which use tricks, so to speak, or some deep insights to make the convolutional neural networks work better and enhance their performance. The first one we would like to introduce to you is the VGG, and it was proposed by the Visual Geometry Group at Oxford University, hence the name. And the idea was to define blocks of convolutions. So instead of thinking about layers, we are thinking about groups of layers, which can be repeated and reused. And this was kind of groundbreaking at that time because it allows for efficient reusage, and the design of the CNN will be much more compact, which is quite nice. And the group also showed that using this architecture, so these block architectures, it's generally better to use several layers of narrow convolutions. So let's say 3x3 or 5x5, compared to fewer layers, but with wider convolutions. So here on the right, what we see is a VGG block, in which we would have several 3x3 convolutional layers, followed by a max pooling layer with a stride of 2. And then we will just add these blocks one after each other. And at the end, again, we would have a fully connected part to get our outputs. The next model is GoogleNet and the Inception Block. It won the ImageNet challenge in 2014. And what this model really did was to propose what's called an Inception Block. And presumably it's based on this Inception movie and the quote, "We need to go deeper." I found a meme for you here on the right. And what the authors tried to solve is the question, what kernel size is the most suitable for our tasks? Because up to that point, everything from 1x1 to 11x11 was being used, but it wasn't really clear why or how to combine these filters together. So what they did is to use a combination of various sized convolutions. And here on the bottom, what you can see is the Inception block. And it's very equivalent to a subnetwork with 4 subpaths, which extract different types of information in parallel. So as you can see here, the input is split into, or is fed to 4 parts of the Inception block. And at the end, all of the results are concatenated. And here on the right, we have the full GoogleNet model. So it starts off with pretty conventional convolutional layers, followed by 2 inception blocks, a max pool layer, again, inception blocks, pooling layers, inception blocks, average pooling layer, and then a fully connected module. The second last thing we wanted to talk about today is batch normalization layers. And the core idea behind these is that training CNNs is actually quite difficult and tricky. Many things can go wrong when we try to train those types of models. And one prominent issue is that the magnitude of the hidden representation can drastically change from a layer to layer. So the output number you will get after each convolutional layer might increase. And there's also the overfitting issue. So what the authors of batch normalization proposed was to rescale the representation after every layer, or we can choose to do it after every layer, based on batch statistics. And this is this equation exactly. So the idea is to have an input and just calculate the z-score. What we're basically trying to do here is to rescale the input to 0 mean and unit variance. And we can arbitrarily also rescale the score calculated here. So what the batch normalization layer has to do is to learn this gamma and beta parameters. And this will be the input, and this is calculated for every batch. And this batch normalization layer is a bit of a controversy because it's working very well and it's used very widely. But the problem is that the theory behind it is not well understood. the authors didn't propose a very solid theoretical derivation, and it's mostly based on intuitions. But nonetheless, the layer itself works very well, which is really nice. But there is this blind spot that we don't really understand why batch normalization works that well. And another issue is, or if we can call it an issue, is that Google has a patent on this layer. So it was accepted. So every model which uses this batch normalization layer is at risk of infringing those rights. So just a thing to keep in mind. But I don't think there's any worries, so to speak, since really these batch normalization layers are used all the time almost. And the last network that we wanted to present is residual networks. The motivation behind it is a little bit tricky, mathematically speaking, but to just give a high level motivation of it is that when we add layers to our model, what we want to try to find is this optimal F here. But when we start to add layers, it's possible that our model is actually drifting apart from the optimal solution. And this is because it's not part of what's called non-nested function classes. And ideally, what we want to have is this situation on the right, where if we added more layers to our model or more complexity, we wouldn't really lose the initial model itself. And what that means, mathematically speaking, is that the identity or the initial tensors should be retrieved after the operation. So implementation wise, we can ensure that the identity is still preserved by introducing what's called a skip connection here on the right. So this is on the left what a normal convolutional layer would look like. And here on the right, it has the skip connection where the input basically can jump, oh, sorry, the input can jump ahead here. And what the model needs to do is learn this fx minus x part, and that's what's called the residual, and therefore the name for residual network or ResNet. Okay, thanks everyone.